Alright guys, welcome to Pre-Calculus 115. So we're going to be going over basically two story problems today. Um, Again, the focus isn't, hey, can you do this specific problem and memorize these specific steps? This is really a focus on problem-solving techniques and ways that you can approach a problem. So I'm going to have you guys approach both of these problems first on your own, try your best. I'm going to give you some kind of guidelines here for just solving any problems, not necessarily these ones specifically. So they can here draw a picture or a diagram, especially when you're talking about like spatial things like areas and volumes and stuff of that nature. Picture can really help you have a point of reference. Like make sure you're having things labeled and you don't get things mixed up or confused. You also want to define variables you're going to use. So you might want, in this case, in this problem, you want to label what your surface area is, what your height is, length, width, those kind of things. So find all the variables which are being used, label them, and see which ones you're kind of missing and which ones you still need. And then just try it out. You need to start doing things. The worst thing that you can do is just kind of sit there and stare at it. Just try and work with it, right? You have a lot of tools at your disposal. You can always be grabbing things. You can use your kind of algebra skills on things, your geometry properties. You have a lot of tools at your disposal. Some of them may be more helpful than others at different times, but just try something. And that's the kind of best that I can kind of ask. So I want you guys to read problem 40, give it a shot, pause the video, try that out, and then once either you think you have the answer or you get kind of stuck and you don't really know where to go anymore, then go ahead and resume and I will go over my way of solving the problem. So go ahead and pause and stop, and when you're ready, we're going to go now. So, all right. So the problem here is we know what the volume of the box has to be, and we are trying to minimize the surface area of the box, which is actually a fairly common thing for companies to do. If you're trying to ship a lot of product, you typically want to minimize the amount of packaging which you need to ship that product. Like it doesn't, like a few bits of extra cardboard really isn't that much money, but if you're shipping thousands or millions of these products around, a few extra pieces of cardboard adds up quite a bit. So you can actually end up saving quite a bit of money by minimizing your packaging. So that's kind of where this is kind of coming from. Again, it's a much more simplified version of that type of problem, but that's kind of where this is at. So I'm going to switch over to this view because I want to go over kind of how I would approach this problem. So I'm going to first just kind of draw out my box. So it's some kind of an open topped box. My pen is slowly dying, so I might have to change to a different pen. So it's going to be a little bit of purple, but mostly blue box now. So there's my open-ended box, right? And we're going to have a height, we're going to have a width, and we're going to have a length of that box. Now, pieces of info that I'm being given, the first key one is that the length is twice the width. So this length is equivalent to just saying 2w. Now why I really like that is because, well, that's one less variable that I have to worry about, right? I can just call this w and 2w, and I don't have to worry about the lengths. A height, I have no way of knowing how that height is related to the width at this current moment. So I'm kind of going to have to wait on that one. So I currently have two variables, which is telling me that I'm going to have two equations, right? So the first thing that I know, or first equation that I can really write, is dealing with the volume. Now my volume is going to be 4,500 cubic centimeters, or cc's. So volume equals length times width times height. So my volume here, which is 4,500 cc's, is going to be equal to my length, which is 2w, times my width, which is w, times my height, which is h. Okay. So I can clean it up a little bit and say, hey, it's 2w squared h, but I can do that later on. It's not a big deal. So that's the first bit of info that I have, which is great. And the only problem is it has two variables. So I really can't solve for w or h because that's the only piece of information that I have. I could isolate them, and I'm going to, but it's not quite yet. Now what I'm actually trying to find, what my actual solution is hey, what's the surface area of this box, right? So my surface area that I'm trying to minimize is going to be, if I draw this out as a net, right? My box is going to look something like this. So think back to the kind of idea of cutting out the corners of a piece of a rectangle, and then you can fold it up and build the box there. So this would be a height, this would be a width, this would be a 2 times width, or my length, right? So I really have a series of 5 rectangles here that I can find the area of each of these 5 rectangles. So the one over here is just a W times H. This middle one is going to be a W times 2W. This is a W times H. This is a H times 2W, and this is an H times 2W. So that's just me doing length times width of each of those 5 rectangles. Now I want to talk about a little quick thing that comes up with this particular problem. They don't really specify if the surface area of an open-ended box, are you counting the interior surface area as well as the exterior surface area, or just one of them? It doesn't change the process in which we solve this. Basically, it would just double your surface area. So you still get the same idea there. So don't stress out too much about that. It's going to be the exact same kind of solution as we kind of go through it. Just that is a thing that people come up. So I'm going to do it as if I only care about the exterior surface area, just because it saves me from doubling things. But you would get the exact same process and solution if you did it by the top and bottom, or the interior and the exterior surface areas being the total surface area. Okay, so what I know about my surface area, I'm going to use the variable, they typically use a capital S. I typically use SA just so that I remember it's surface area. I can use 2 letters for that single variable. So my surface area is going to be equal to 2 of the WH's, so 2 W times H's. I need 2 H times 2 W's, so I need to add 2 W plus, or times H's. And then I need to add a single W times 2W. Okay, so that's going to be my equation for my surface area. So I can clean that up a little bit. I'm going to go ahead and do that now. So my surface area is going to be, this is 2WH. This would be 4WH. And then this would be 2W squared. So that's going to be my surface area equation right now. So problem is here, again, I have W's and H's. But using my volume equation here, I can actually isolate either W or H here, and then I can sub it into this equation, and then I'm only going to have one variable, which I can then use to optimize the problem. So my ultimate question is, what is the height of the box that I need? So I would likely want to get just H's here, which would mean that I would need to isolate the W on this equation here, which would work. I'm not going to do that though, because I can see right now that this is 2W squared. If I try and isolate this H, I'm going to get W squareds. You can do it. Sorry, if I try and isolate the W, I'm going to get a square root of H's, which works, but it's not going to be easier. If I isolate the H, then I'm just going to have one extra step at the very end, but that's a lot easier in my eyes than trying to work with that radical for a good portion of the problem. So both work, but that's just my rationale for why I'm doing this. So I'm going to isolate this H. I just need to divide both sides by 2W squared. So I would get H is equal to 4,500 divided by 2W squared. So I could reduce that to being 2,250 over W squared. I'm not going to because I can see that, hey, this, once I plug this in for the H here, the 2's are just going to cancel. So why reduce it and then just unreduce it? Likewise here, the 4 and the 2 can reduce a little bit easier there. So you could really say it's not going to make it bad or wrong or anything. It's just, you're just going to end up undoing it. So I'm going to not even bother. So I can now plug this into my H's here and here. So I now have a new equation for my surface area. My surface area is going to be 2W times 4,500 over 2W squared plus 4W times 4,500 over 2W squared plus 2W squared. So off the bat, this one here, I can reduce that. The 2 and the 2 are going to reduce out. This W and one of those W's will cancel out. Over here, this W and one of those W's, and then this 4 and this 2 will reduce to just a 2. So cleaning all of that up, I'm going to end up with a surface area of, this is just going to be 4,500 over W, plus, well, 2 times 4,500 is going to be 9,000 over W, plus 2W squared. So that is my equation for surface area. Now, I might say, well, how do I solve that, right? Well, it technically has two variables. It has the surface area and the W, but I'm trying to optimize. I'm trying to find the smallest surface area possible. So what I actually want to do is I want to graph this, right? So you may say, well, I could combine these, and yeah, you can, and that's fine. You get 13,500 over W. But what you'll see is you can say, well, do I need to simplify it? You can, but your calculator doesn't really care. So when we go over to Desmos real quick, we're just going to graph that. So again, I could do it as 13,500 over W, but I'm just going to leave it as is, just so you can keep the same idea. Plus 9,000 over W. Oh, sorry, I can't use W's. I have to use X's on Desmos. Desmos doesn't like other variables being used. You can do it, but just a bit more of a pain. Plus 2x to the second. Okay, so I graph that, and hey, I see nothing. Well, that's because these are some pretty big numbers. I'm going to have to do a lot of zooming out before I can really see anything. Well, there's part of it, but that's negatives, which I really don't care about. Zoom out. Zoom out. Oh, there we go. Right. So here's the part of the graph that I actually care about. Right. I'm seeing it dip back down and then up, and I'm looking to have the smallest surface area possible. I don't care about the stuff over on this side, even though it is lower than this, because it's on a negative value. So that would say, hey, my width would need to be negative, which would give me a very, very small surface area, but that's not really what we're looking for, because it's not a realistic thing that you could actually do. So again, to make sure you see the dot, if you click on this, you can actually get the dots to show up. So you click on that and say, hey, you get a dot there of 15 and then 1350. So context-wise, what does that mean? So go ahead and in your head say, what does the 15 mean? What does the 1350 mean? Well, let's refer back to this, right? Effectively, I have made my surface area my y when I graphed it, and my w's were my x's when I graphed it. So that means at any point, the x-coordinate is going to be my w, or my width, and the y is going to be the surface area. So what this is showing me is, hey, the lowest surface area that I can get, which is my lowest y value, would be 1,350 square centimeters. And that would happen when I had a width of 15 centimeters. Okay. But again, my ultimate question wasn't that. My ultimate question was, hey, what height do I need? So let's head back over to this. Right? So we found that the point is going to be the point 15, 1350. So to find the height, which is going to give me that, I can really just take this height, and this width, and plug it in here, because this is solved for height, right? So if I do height equals 4,500 over 2 times 15 squared, excuse me, 225, double is going to be 450, so this ends up being h equals 4,500 over 450. That should be very, very easy for us to reduce. We get a height of 10 centimeters. So there's the kind of process there. Again, if you solve this a little bit of a different way, but you still got that same solution, awesome, great. There's a lot of different ways to approach this. This is just one of the ways that we're going to kind of expect you to kind of go towards, because this is going to be going towards a lot of stuff we've been doing like in the past last year. We're going to be doing a lot more of this kind of optimization stuff, which is what this is called in the future here. Okay. So hopefully you're feeling a little bit better on that. Again, I'm not expecting you to be an expert on that, but if you follow along with what I was doing and that kind of made sense, you're in the right spot. Okay, so go ahead and try number 42. So again, pause the video, give it a shot, see what you can do, and then come back here and unpause it, and you can watch me go ahead and do this one here. All right, so I'm assuming that you have tried it out on your own now. So I'm going to pull up my document camera, got a fresh sheet here, and we're going to approach this problem. So again, I want to start by drawing out a picture here. So I have 300 feet of total fencing that enclose 2 identical rectangular pins and share a common fence. So what that basically means is I'm going to have a big rectangular pin. This is like a very cliche kind of very common problem to see. So I kind of have pins that look like this, right? I have my fencing going around the outside, and I have one middle divider, which gives me 2 separate pins. It's a pretty common way to kind of more efficiently build separate enclosures, because now they can share one wall versus me building 2 separate rectangles and having to build that wall twice effectively. So that's what I got. So I can kind of start by labeling things, things that I know. So this is going to be, I'll call this my length. This is my, I'll call this a width, this a width, and I'll call the whole thing 2W. I could have done the width as the whole thing, and then these are each half a W, but why add fractions if you don't have to, right? So the first thing that I know is, hey, what's my total perimeter, my total A amount of fencing? Well, I have 2W plus 2W, which is 4W. So 4W plus length, but wait, there's a third length, so plus 3 lengths equals my 300. Right? And then my first question here is I'm trying to get the pin that has as large of an area as possible. Okay, so area of this pin would be just length times 2 times W, right? We're going to disregard the loss of area of the fence line in the middle. It's a negligible area, but in reality you would be missing an area that is the width of the fence. If you want to make the problem that much harder, go ahead, but it's very, very slightly going to change the actual outcome, and you would need to know the width of the actual fencing. So we're going to disregard that one. Okay, so my area here is just length times 2 width. So I can try and isolate either the length or the width here, whichever one I feel is going to be nicer. It doesn't really matter. I'm going to go ahead and isolate the length. So I'm going to subtract 4w over, divide by 3, and I would get the length is equal to 300 minus 4w all over 3, which is going to be length is equal to 100 minus 4 thirds w. So I've gotten my length in kind of by itself in terms of w. So what I can do with that now is I can take this whole mess and substitute it in for the length up here. So doing that, I now have an area is equal to 100 minus 4 thirds w times 2w. And that is an equation for area with only one variable, meaning, hey, once I'm here, I'm trying to optimize this. I'm trying to find the largest area possible. So I can go ahead and graph this and find where that graph kind of peaks out. So let's head back over to Desmos. Let's get rid of the last problem. Let's put in our equation here. 100 minus 4 thirds x, and again I'm using x's as opposed to w's just because Desmos prefers x's, and then times 2x. And then I'm going to do a lot of zooming out because this is going to be a pretty large thing here. And there we go. And I found that kind of peak right there. Right? So on this one, my answer there was 37.5, 3,750. So then if I hop back over to this view, what does this mean in context, right? Well, here, my y was my area, and my x was my width. So this is saying, hey, my highest area would be 3,750 feet or square feet. And then to get that, I would need a width of 37.5 feet. So that is kind of one of my dimensions. Now to get the other dimension, to get my my length, I can just take that width, plug it in here. So if I do 4 thirds times 37.5, and then I do 100 minus that, well, 100 minus 50 is going to be 50. So then I would have a length of 50 and a width of 37.5 would be the dimensions of this particular pen that are going to give me my optimal area. All right, so let's head back over here real quick. So then B, if X represents the length of the enclosure, what is the dimension, what is the domain in the context of the situation? So I think I actually did mine in terms of width. So let's change that up real slightly just so that I can actually answer that quick question in particular. I'm going to do it first for what I did, which is solving it for the width. Context of this, the domain, which is everything that is possible, would be between 0, because if I went to 0, my area is 0, and then 75. Okay, because I don't care about anything down here, which is going to be in the negative area. So my domain in width's context would be any value between 0 and 75 works. Right? So if I want to change that to the length context, I'll do that real quick. All we would really do is, as is here when we solved this for length, we want to solve it for the width instead. So I would get W equals 300 minus 3L all over 4. So then I could plug this in for the W there, and I would get A equals length times 2 times 300 minus 3L over 4. Now the 2 and that 4 are going to reduce down to just a 2 on the bottom. So that would be what I would end up graphing. So let's go ahead and graph that, just so that you guys can kind of see. That's partially on me, but hey, I'll use the x-axis, and now you can see it two different ways. I want x times 3, I should put that in parentheses again, 3x, or sorry, 300 minus 3x over 2. So on this one, this green graph is going to be my values as far as the length goes, which is again it's going to give us the exact same area as the last one. But now we're saying, hey, there's where my length would be 50 as opposed to the 37.5, which we got when we did the width. So there you go. And then context of the domain here, I would only once again care what values, this is really slow, what values are going to be positive or above the y-axis here, which is going to be between 0 and 100 for that value there. All right, so back over, I want this view here. Okay, so that is it for today. Just really kind of two problems again. The main focus isn't can you solve this exact problem, memorize these certain steps. That's not at all what I want you to do. I want you to think about what actual strategies did we use. So the big strategy that I want you to kind of become more and more familiar with as we kind of go through the year is trying to get equations, and if you're trying to find, hey, what's the largest, what's the shortest, what's the biggest, whatever kind of optimization is what those kind of problems are called, you want to try and get an equation for that particular thing you're trying to optimize or find the highest or the lowest or whatever of. That only has one variable in it. Once you have that, you want to graph it, and then you can use the graph to find that exact point. There are algebraic ways of finding that exact point, but that's what calculus is, so we're not quite there yet. We're just going to be kind of cheating and using the graph in order to do that. So that's the big strategy that I wanted you guys to get out of today. So hopefully you feel a little bit more confident with doing that than you did before we started. So with that, here is our homework for today. We're going to do 45 through 51, and I will talk to you guys next time.